Chapter 6, which is about process energy calculations based on energy balance equations. The most important keyword of this chapter is energy balance equations. This energy balance equations is very similar to the material balance equations, specifically total mass balance equations. So let me check the total mass balance equations. Generally, accumulation is equal to in minus out plus generation minus consumption. However, when you are thinking about total mass, you don't need to think about generation and consumption term. So, here is the differential form of total mass balance equations. dmdt, this m is the mass of the systems, is equal to the summation of all input minus the summation of all output of mass. Of course, we cannot imagine the mass generation or mass consumption in terms of total mass. Also, this differential form is converted to the integrated form like that. Initial mass minus, final mass minus initial mass in the system is equal to summation of input minus summation of output. Of course, this quantity should be integrated over time. That was the total mass balance equations. Energy balance equation, exactly the same. The energy of system dt is equal to all input minus all output in terms of the energy flow rate. Its integrated version here actually the same with the total mass balance equations. Energy balance equations again have no generation and consumption terms, and only a total energy balance equation is available, not a component energy balance equation. Okay, so only what we have is total energy balance equation. So here is the differential form of energy balance equation, and let me explain about the energy flows. Dot E sub J flow. Here is a big pot, and into this big pot we have two methods for the energy transfer into this system. The first one is the energy transfer through material transfer. Let me pour a cup of hot water into this pot, and then materials are introduced into the pot, and also at the same time the hot energy are introduced into this pot. That is the first type energy transfer. That is the energy transfer through material transfer, or material transfer based energy transfer. The second one is without material transfer. You could heat directly this pot, so the content inside of this pot would be heated. That is the second type, which is direct energy transfer from the surroundings into the system. Okay, here is the same explanation. Here is the schematic diagram of the system. So we have some energy inside of a system, and some energy transfer is available through energy flows. The solid line indicates the first type of energy transfer. Again, mass transfer based energy transfer. Mass in, carrying energy in. The same. Or mass out, carrying energy out. The same. And let's go to the second type energy transfer. It could be heat or work, or sometimes heat out. So work and heat can be belonging to the second type electron transfer. So let me read this sentence. Energy flow across system boundaries are two types. The first one, material flows in and out of the system, open system. Through these material flows, the energy is flowing in and out to or from the system. The other thing is energy flows via heat or work. In the case of a closed system, even in open system, you could directly heating this system. Let me define specific energies. Specific system energy is caret E with subscript system. It means the specific energy of system, which is energy per mass or energy per moles. That is the specific system energy. How about specific stream energy? Caret E J flow is equal to the energy flow of J stream per mass flow rate of the same corresponding stream. Or sometimes you could use the moles instead of mass. Here is the property of energy, very important thing. Energy is a function of the state of the system or the stream. Shortly, energy is a state function. Let me emphasize, state function, independent of pathway. You have learned about that in your general chemistry, but anyway, I'll review it later. The numerical value depends on the chosen reference state of a system. Energy has not the absolute value. It is always evaluated with respect to the other reference value. The third one, the state of a system. I have said energy is a state function. What is the state? The state of a system can be identified by velocity, position, mechanical properties, but usually we didn't use this one. And more important state variable is pressure, temperature, phase, composition. P, T, phi, X. Maybe you could expect it. How to quantify the specific energy? Method 1. If you have a data, you could use it. So sometimes you can find the data of your interest from table or chart. Then you could quantify the caret E or specific energy. It's very similar to the phase equilibrium calculation in the separation part. If you have a phase diagram, it is the best. Just you could read some values about the composition, and also you could calculate the amount of each phase by using inverse level rule. You have learned about that in the just previous chapter. Like that, in method 1, we will use the table or chart published in some books or some internet or something. But sometimes, or actually in many cases, you do not have the table or chart. Then what can I do for calculating the quantity of the caret E? Here's the method 2. Define a reference state and set caret E is equal to 0 at this state. This sentence is related to the second properties of the energy. And then find the model equation that describes how caret E depends on the state relative to the reference state. It means we should use the equation. For the phase equilibrium in the previous chapter, Sometimes we have used the equilibrium phase equilibrium equations like the Raoult's law and Henry's law. This method 2 is that case. So I could say method 1 is data method. Method 2 is equation method. So you will learn about those methods for setting up the energy balance equations. Let me explain about the energy term in a more deeper insight. In this slide, I'd like to introduce internal energy symbolized by U and enthalpy. Internal energy is energy stored in molecules in the form of covalent chemical bonds, non-covalent intermolecular forces, and thermal motions. Internal energy can be considered to be split into two terms. The potential energy and kinetic energy in terms of microscopic scale. This microscopic potential energy have covalent chemical bonds and also non-covalent intermolecular forces. The second term, microscopic kinetic energy, has or related to the thermal motion. This internal energy excludes any system energy due to external forces such as system's velocity or its position. That is to say, the macroscopic kinetic energy or the macroscopic potential energy of the system is not included in this internal energy. So only microscopic terms are included in this internal energy U. Of course, internal energy is a kind of energy, so which is the state function. That is a function of pressure, temperature, phase, composition. Pt phi x. Then let's go to enthalpy. Enthalpy, symbolized by H, is the total energy of a thermodynamic system. Then, as you know, enthalpy H, caret enthalpy, is caret internal energy plus PV. Again, enthalpy is the internal energy plus the energy required to make room or space for the system by establishing its volume and pressure. So this second term is usually described by PV term. This is about some macroscopic energy, and internal energy is microscopic energy. Internal energy and enthalpy are defined relative to some reference state. Of course, I have said about the basic properties of energy. U and H are energies, so their values are always estimated with respect to some reference state. Also, they are state function, while enthalpy is state function. Here is the famous steam table. From this steam table, you could find the values of specific enthalpy, like caret H, in kilojoule per kilogram, and specific internal energy, caret U, plus specific volume, cubic meter per kilogram, of water and steam, or water vapor. So it is called steam table. Here is reference data, which is liquid water at each triple point. That is to say, temperature 0.01 Celsius degree and pressure 0.00616 bar. Let me try to read this steam table. So let me say this is y-axis. y-axis is the pressure, and x-axis is the temperature. So here's the temperature value, 50 Celsius degree, 100 Celsius degree, something like that. So temperature increases along the direction from left to the right. And let's go to the very first column, that is the pressure. If you after you fixed the temperature and pressure, and then you will try to find the pressure value in this column. So for example, here 0.00616 bar, here's the bar, and next one 0.1 bar, 1.0 bar, up to 10 bar here. And below the pressure values, you can find some parentheses, and inside of which we have some value. That is the saturated temperature in Celsius degree. As you know, we have one component system here because we are thinking about only water, and phase have two phases at liquid and steam or vapor. So let me calculate the degree of freedom by Gibbs rule. C minus 2 plus the number of phases, so 1 minus 2 plus 2. So degree of freedom is just 1. It means if you specify the pressure, then temperature is fixed, right? So at equilibrium, the temperature is fixed after you specify the pressure here. So this value is about the saturated temperature at the given pressure. Here 0.006116 bar, then it means the pressure of triple point, and of course the saturated temperature is fixed, 0.01 Celsius degree. That was the reference state. So in this region, we have the information about enthalpy, internal energy, and specific volume at the equilibrium of this pressure. So at this pressure and temperature, you have two phases, right? Because we are on some equilibrium between multiple phases. This column is devoted to the saturated liquid, and the second column, saturated vapor, on the equilibrium line. So how about the enthalpy value and internal energy value for the saturated liquid? Of course, for the liquid, they should be 0 because we have taken this temperature and this pressure as the reference point, and also the phase was liquid water as the reference state. So those two values should be 0. And specific volume here, and in the saturated vapor phase we have some values, right? I mean, we should have different values of enthalpy and internal energy in terms of the enthalpy and internal energy, right? Okay, then let's go to the other pressure. Let me say 1.0 bar. Then the saturated temperature is fixed around 100 Celsius degree. Actually, that is the boiling point, right? And then we have some values of enthalpy, enthalpy, internal energy, and specific volume for the liquid phase, and also the same thing for the saturated vapor phase, because at this temperature and pressure we are on the equilibrium between liquid and vapor. Then let's go to temperature variable region. Then still we are on the 1 bar, and temperature is not the saturated temperature. In this case, 50 Celsius degree. We are below the saturated temperature, so we should have only one phase. We are not on the equilibrium in this temperature region. At 50 Celsius degree, which is below 100 Celsius degree boiling point, then we have only one phase, which is liquid, and this is the data for liquid, unsaturated liquid. This value for the enthalpy, this value, internal energy, this is the specific volume. Then let me increase the temperature. Right now we are on the 50 Celsius degree here at 1 atmospheric pressure, actually 1 bar. Then we are going to 100 Celsius degree here. Before 100 Celsius degree, we are passing the boiling point, right? Saturated temperature, in other words. So at this point we are on the equilibrium. Then after passing this point, then all of our water molecules is going to the vapor phase or steam phase. Then those three values are belonging to the vapor of water molecules. Then 150 Celsius degree, 200, then finally 350 Celsius degree. Those 1, 2, 3, 4, 5, 6 column is devoted to the liquid. Vapor, and this is the liquid. So actually this pink region is going to the superheated vapor. However, in this empty region, in terms of color, is going to the liquid, unsaturated liquid region. Here is the summary. From the steam table, you could read the value of internal energy and enthalpy, or moreover specific volume, as a function of pressure, temperature, and phase. In this table, reference state is fixed like a triple point, and at triple point of this temperature, pressure, and phase and composition, then the energy term is going to 0, because we have taken that point as the reference state. At saturated temperature on the first column, there is a big difference of enthalpy and internal energy between liquid and vapor, of course. Also, there is a big difference of enthalpy and internal energy between below and beyond saturated temperature. Here's the saturated temperature. Before the saturated temperature, the enthalpy value and internal energy value is just 200. However, after this water molecules is going to the vapor phase region, then those values is going to about 2500. It's a big difference at the interface of the phase change. And as temperature goes up, those energy values are steadily going up to 675 and about 3000, something like that. However, the biggest difference or jump up in terms of enthalpy and internal energy was found at boiling point or saturated temperature. Here is an illustration. Liquid water at 1 bar and 99.6 Celsius degree is saturated. How can we recognize it? Here, 1.0, 99.6 is indicate we are on the equilibrium. It means water and vapor is saturated. And you could read the enthalpy value and internal energy value from here. For the liquid water, 417.5, 417.4. And let's go to the temperature region, temperature variable region. Water at 200 Celsius degree. Try to find 200 here in this column, and 10 bar. So let's go to the 10 bar here. We are on the liquid or vapor or superheated vapor, and the value of enthalpy is this one, and internal energy this one. Please try to read this steam table. Practice and practice. Here is the full stream table for your information. Temperature the same in the previous slide, but the pressure data is extended from 10 bar to about 220 bar. So please check this table for your calculation in the process. How to calculate the values not reported in the table? In that case, you could use the linear interpolation. For example, here is the steam table. I have captured a portion of the steam table. Then you want to calculate you want to obtain the value of enthalpy at 1 bar at 125 Celsius degree. So you should find some values between the enthalpy at 100 Celsius degree and enthalpy at 150 Celsius degree at 1 bar. So how could you calculate it? Let me represent this situation by using some graph. Axis is temperature, 100 Celsius degree, and this is the 150 Celsius degree. And also, at each temperature, you could have the enthalpy value, like 2675 or 2776, so like that. And what you want to obtain is this data at temperature T, and you should get this value. So if you can draw this kind of graph, then plot the present data and then just draw some line and then find the value. Or you could use some proportionality equations, like this is the unknown values of H, and H1 is like enthalpy at T1, and enthalpy at T2 minus enthalpy at T1 is equal to the temperature differences, like T1, T2 minus T1. Then you could calculate the unknown enthalpy. This equation is exactly the same as drawing some lines on this plot. So please exercise by using this example. Okay, so we have a steam table, and then let me plot those data on the graphs. Here, x is the temperature and temperature, y axis is the specific enthalpy in kilojoule per kilogram. Also the same thing, specific enthalpy or internal energy in kilojoule per kilogram. Then let me check the first left curve. We have three different isobaric curves or constant pressure curves. The first one is this one, following this line, and then 1 bar, then like that. It means this curve is obtained at 1 bar, so the boiling point temperature or saturated temperature at 1 bar is around 100 Celsius degree. So around this temperature, liquid is converted to vapor. So at this vertical line, you have an liquid vapor phase equilibrium. Then let me change the pressure to 10 bar. So the liquid line is extended, and then at the saturated temperature at 10 bar, like I think about 130 Celsius degree, then the specific enthalpy value is going up, jump up, and then steady increase as a function of time, that function of temperature. So here is the liquid, here is the vapor. At this vertical line, you have a liquid vapor equilibrium. How about 100 bar? Shift to about 315 Celsius degree for the equilibrium. Then the steady increase in the vapor phase of specific enthalpy. Okay, that is the first graph. And the other thing is we will compare between the specific enthalpy and specific internal energy. At low temperature, enthalpy is approximated by the internal energy. It means the PV term would be neglected for temperature. However, after boiling point, okay, this graph is obtained at 1 bar. So the boiling temperature or saturated temperature is around 100 Celsius degree. And after the boiling point, we have very high values of enthalpy and internal energy. The difference between the temperature beyond the boiling point and below the boiling point is the gap between enthalpy and internal energy. At higher temperature, the gap between enthalpy and internal energy cannot be neglected. Why? At lower temperature, enthalpy is approximated by the internal energy. It means at higher energy or in vapor phase, you should think about the PV term for calculating the enthalpy. However, at liquid, the temperature dependency of liquid is very small, so PV term could be neglected at lower temperature. So let me summarize those characteristics extracted from those two graphs. First, at a change in phase from liquid to vapor, like that 1 bar, vertical line at 10 bar, vertical line 100 bar, large increase in internal energy and enthalpy is observed, of course. So it means vapor phase is much more energetic than the liquid phase. At a fixed phase, internal energy and enthalpy increase linearly with an increase of temperature. Increasing. Not like this big jump, but steady increase is obtained in any phases as temperature increases. I have said about the PV term from the second graph. Liquid, you could neglect the PV term. However, in the vapor phase, PV should be considered. In both, one more thing, in both low pressure vapor phase and liquid phase, the internal energy and enthalpy is not the function of pressure. Let's go back to the first graph. Look at the liquid. There are no difference between 1 bar and 10 bar in this part, while there are no difference between 10 bar and 100 bar. So for the liquid phase, the energy terms is not the function of pressure. Okay, actually, the liquid phase is not dependent on pressure in terms of volume or something. So like that, energy term is not the function of pressure at liquid phase. One more thing. How about the low pressure vapor phase? Look at that. There are no big difference between 1 bar and 10 bar in vapor phase. Relatively lower pressure. However, when you increase the pressure from 10 bar to 100 bar, you could find a significant decrease of the specific enthalpy. So, again, in both low pressure vapor phase, like 10 bar, 1 bar or something, and liquid phase like that, the energy term is not the function of pressure. Okay, example 6.5. Let's use steam tables. Here is the situation. Uh, Here is a pump, and you are pumping some water to more pressurized water. So let me check these state variables. 60 Celsius degree, 5 bar liquid here, 5 bar water here, and the flow rate is 1.5 kilogram per second for the input stream. How about output stream? The same flow rate and the same temperature, but after pressurizing, you would have a higher pressure of the same material. So let me calculate the enthalpy flow change between output stream and input stream. So I'll calculate or obtain the value about the enthalpy for input first and then output first. Then calculate the change between output minus input. So let me start with the input. The state variable is 5 bar and 60 degree. So let's go to the steam table. Here is a portion of steam table which is appropriate for this calculation. So 5 bar, okay, great. I could find 5 bar in the y-axis of the steam table. And then 60 Celsius degree. Unfortunately, we have the data at 50 Celsius degree and 100 Celsius degree. The data we want to have is between this column and this column. Then how can we obtain the unknown values of enthalpy and internal energy term? No data at 60 Celsius degree. Use linear interpolation introduced in the previous slide. So we could use 5 bar 50 Celsius degree here and 5 bar 100 Celsius degree here. Both of them is liquid, right? Then by linear interpolation, you could calculate the enthalpy value at 5 bar and also at 60 Celsius degree. So specific enthalpy is here for the input. In the same way, we could calculate the output data. So 100 bar, you can find it, but unfortunately still we are on the 60 Celsius degree, which is between 50 and 100 Celsius degree. Use the linear interpolation. Then you could find this value. Then finally, you obtain this value. Then the enthalpy change is this value for the output, and the enthalpy change is output here minus input here. So that is the about 8 kilojoule per gram, and we want to calculate the energy flow instead of specific energy change. So the difference by molar the mass flow rate for each stream is like that, 1.5 kilogram per second with the difference. So finally we obtain the value 12 in kilojoule per second. That's it. Example 6.7, using enthalpy composition graphs, ammonia water mixtures case. In the previous example, we have used the steam tables. Then we have obtained the values from the table. In this example, we have a phase diagram, fortunately. So we'll use this phase diagram. X-axis is the mass fraction ammonia, that is to say kilogram ammonia in kilogram solution, where the solution is a mixture of ammonia and water. Y-axis is specific enthalpy, kilojoule, kilogram solution. We have 3 different lines here, or curves here, and each curve is obtained at constant pressure. This one is obtained at 0.1 bar, the second one at 1 bar, and the third one at 10 bar. Also, each constant pressure line, you could find some temperatures. Highest temperature like 313K, then 293K, and then finally 233K. That is to say, the temperature decreases along this constant pressure curve. Also the same for the 1 bar and 10 bar. Let me focus on the first 0.1 bar graph, and this curve means the equilibrium between liquid and vapor of ammonia water mixtures. So below this curve at 0.1 bar, you could find a single liquid phase. Above this curve, you could find vapor phase. I mean one single vapor phase. However, the boundary between liquid phase and vapor phase, you could find some equilibrium between liquid and vapor. Let me increase the pressure from 0.1 bar to 1 bar. Also, the same. This curve is about the equilibrium between liquid phase and vapor phase. So, below it, you have a single liquid phase. Above it, you have a single vapor phase. The same for the 10 bar. And this dashed line is the line connecting the same temperature. So this is 313K, also 313K, also 313K. It means the dashed curve indicates the constant temperature lines. Okay, let me use this phase diagram, and then let me try to get some enthalpy values about some specified temperature and pressure. One more thing here. Whenever you look at some tables or phase diagrams, you should think about the reference state. In any cases, reference state is defined. In this phase diagram, pure liquid water at 273K and pure liquid ammonia at 196K at 1 bar is the reference state. Okay, let me go to the first question. Obtain the specific enthalpy of liquid water at each melting point. What is the melting point of water? At 1 bar, the temperature is 0 Celsius degree, or 273K. So, what is the value of this enthalpy? It's time to check again the reference state. Pure liquid water at 273 Kelvin is the reference state. It means this enthalpy at reference state, because pure liquid water here and melting point is 273K. Therefore, the enthalpy of this situation is 0, because we are saying about the reference state of this phase diagram. The number 2 question, enthalpy of a saturated ammonia solution at 1 bar and 293K. Saturated means we will read some values on the curve of phase diagram at the specified pressure and temperature. So let me go to the 1 bar curve and try to find the 293 Kelvin. Where is the 293 Kelvin? Here. Therefore, the enthalpy of this point is read at the y-axis of this point. That is to say, minus 140 here, kilojoule per kilogram solution. Also, you could expect the composition of ammonia. That is the 0.34 mass fraction ammonia. Let's go to the number 3 question. Enthalpy of a saturated solution. Also here is the saturated. It means you will read the point on the curve of equilibrium. Saturated solution of ammonia and water at 34 weight% ammonia and 10 bar. So where is the 10 bar? Here, and 34% is here. That is to say, you could read this the value of enthalpy at this point. That is the plus 200 kilojoule per kilogram solution. Number 4 question. The change in enthalpy, that is the target, associated with mixing 2 liquid. The first liquid is 1 kilogram liquid water at 1 bar and 373 Kelvin. This is the first liquid. Again, 1 kilogram liquid water at 1 bar and 373 Kelvin. The second liquid is 1 kilogram of an 88% saturated ammonia solution at 1 bar. We mix together those solutions and liquid, then we'll calculate the some energy term about the liquid mixture. Let me start with the first liquid and then the second liquid. So for water at 1 bar and 373 Kelvin, we could read the value of the enthalpy from the phase equilibrium lines. Where is 1 bar line? Here, and then let's go to find the 37 Kelvin along this curve. Here. That is to say, 1 bar and 373 Kelvin indicates pure water, because the composition of this point is 0 of ammonia. That is to say, HW, enthalpy of water, of this condition is 405 kilojoule per kilogram with 1 kilogram. Let's go to the second liquid, which is the solution. That is the here for saturated liquid ammonia at 1 bar, 88%. So 1 bar and 88%. So the value of enthalpy is minus 260 kilojoule per kilogram. Here by 1 kilogram. So total energy sum of the mixture is 145 kilojoule. That is the first enthalpy. Then we'll calculate the enthalpy of the mixture. Again, H1 is the summation of enthalpy of each liquid or solution. So we have got some simple summation of those two things. However, the composition become changed after mixing. So at the very first time, 80% ammonia is there. 1 kilogram water plus 1 kilogram of the solution is going to 48% ammonia in the mixture. The composition of ammonia is going to the half of the original value because the mixture is 1:1. Then let me try to find the enthalpy value of this mixture. So at 1 bar and 48% here at this point, you could read the value of the specific enthalpy, that is the minus 200. Okay, and the amount of this mixture is 2 kilogram. So H2, I means the enthalpy of the mixture is 2 kilogram by minus 200, going to minus 400 kilojoule. Then Target is the change in enthalpy, so H2 minus here, H1 here, then minus 400 kilojoule minus 145 kilojoule, then which is going to this value. That is the answer for the number 4 question. Until now, for calculating or obtaining the values of enthalpy and the internal energy, you have used tables or charts. However, sometimes you cannot find some data tables or any phase diagrams. And what can you do in this situation? When we don't have tables or charts, use model equations to calculate the change in enthalpy or internal energy. The next sentence is very important thing. When only one single property is changed while holding all other properties constant. It is impossible or sometimes it is difficult to calculate the change in energy term when multiple variables are changed. So you will try to calculate the change in the energy term when only one property, sometimes pressure, is changed while holding all other properties constant. When you have a plan to change pressure, then you should fix temperature, phase, composition. Or when you change the temperature, then you should fix pressure, phase, composition to calculate the change in internal energy and enthalpy. Let me start with change in how to calculate the change in enthalpy and internal change with the change in pressure. Then we'll go to the, of course, temperature and phase and composition. This is the starting point in terms of pressure. For ideal gases with change of P1 to P2 at constant temperature, phase, compositions, that is to say all other properties constant. Then for ideal gases, the internal energy is not changed with pressure, and enthalpy does not change with pressure. It means internal energy and enthalpy are not function of pressures. Or in this case, I have said about the ideal gases. Also, this is the good approximation for real gases at small pressure change or at low pressure. So in those cases, the enthalpy and internal energy is independent of pressure. How about for solids and liquids? Especially in liquid phase, the internal energy is still independent of pressure. However, enthalpy change should in the case of enthalpy change, you should think about the PV term. In the case, due to the pressure independent internal energy, so internal energy term is going to 0. So the difference in enthalpy is V P2 minus P1. In this case, specific volume is constant in terms of pressure, and pressure change here. So the pressure change makes the enthalpy change here. Here is the illustration. The specific volume of liquid water at 50 Celsius degree is like that. The enthalpy change associated with increasing the pressure of liquid water at 50 Celsius degree from 1 bar to 10 bar Right now we have changed the pressure. Then we could calculate this way. That is to say, H2 minus H1 is equal to H is going to U plus PV. So U2 plus P2V minus H1. H1 is going to also U plus PV. U1 plus P2V or something like that. But the internal energy should be the same, independent of pressure. So internal energy going to 0, then the difference can be calculated by the difference in pressure with specific volume. Specific volume is independent of pressure in liquid or solid. So specific volume is going to here, and then P2 minus P1 is about 9, and then some changes of the units, then we could calculate the enthalpy change. So the enthalpy change of liquid by pressure change is driven by the pressure change with the constant specific volume. However, in other cases, no changes and no changes. So the pressure effect is relatively weaker than the effect of temperature. So let's go to the temperature. Change. Let me calculate change in energy term with change in temperature. That is temperature. So here is two important equations. The enthalpy change can be calculated by the temperature difference, and the coefficient, the proportionality constant, is constant pressure heat capacity. That is the definition of kind of. So your enthalpy change can be calculated from the temperature difference by Cp, constant pressure heat capacity. Go to the other thing. In this case, I'd like to say about the difference or change in internal energy. Almost the same. However, in this case, you should use the constant volume heat capacity. That's it. Very simple. More generally, the enthalpy change or internal energy change could be described by integral of heat capacity with respect to temperature, because Cp could be the function of temperature. However, in many cases, Cp is constant over a wide range of temperature. So in that case, this equation, the first two equation, is right. However, for gases in large temperature changes, in that case, the constant pressure and constant volume heat capacity cannot be considered as the independent of temperature. So I mean the Cp and Cv should be considered as the function of temperature. So in that case, you should integrate the heat capacity with respect to temperature from T1 to T2, like that. Okay, how can we obtain the temperature function of heat capacity? There are polynomial expressions for the heat capacity of some compounds in Appendix B. For example, here, this is the Cp of CO2, carbon dioxide. It can be described by A plus Bt minus C T square plus D cubic T. Then the parameter ABCD is found in Appendix B. So here is some example. Comes from the Appendix B. compound, carbon dioxide, and um, the room temperature heat capacity is like that maybe, and then the parameter A, B, C, D is listed here. Then you can use these values for the equation A plus BT minus plus C T square plus D T cubic T or something like that. One more thing, relationships between CP and CV, pressure, constant pressure capacity and constant volume capacity. For liquid and solid, Cp is almost equal to Cv. However, for gases, Cp is equal to Cv plus R, ideal gas constant. Okay, here's some illustrations or example. The constant volume heat capacity Cv for liquid water is this value. The specific internal energy change associated with increasing the temperature of liquid water at 1 bar from 50 Celsius degree to 60 Celsius degree is like that. So important thing is you have changed the temperature at a fixed pressure and fixed composition, 100% water, and fixed phase. It is only liquid. So the difference, the change of the internal energy is Cv T2 minus T1, like that, because this is the liquid. Then you could calculate the change of internal energy. Let's go to the gas phase case. The heat capacity of Cp of CO2 is a function of temperature. I have said for gases in large temperature changes, you should consider the heat capacity as a function of temperature. And the heat capacity of CO2 can be described by like that. And this constant value could be obtained from the appendix B. So let me try to calculate it. H2 minus H1 is integration of Cp with respect to temperature from 323, that is the 50 Celsius degree, to 473, which is the 200 Celsius degree, with the function of temperature, which is the heat capacity at constant pressure, dt. Then you could calculate the value of the enthalpy change. Okay, let's go to the third variation. That is the phase variation. Following at the very first time, we have changed the pressure, then temperature, then right now phi, phase. Enthalpy of vaporization, delta the caret H sub V for vaporization. For liquid to vapor is delta caret HV. You could find the value from some data book or something like that. The other thing, enthalpy of melting for solid to liquid, which is called the enthalpy of melting. I mean delta H caret M. So those two enthalpy terms are relevant to the change in phase from liquid to vapor and solid to liquid. Enthalpy of condensation, vapor to liquid, I mean the backward reaction or backward process of the vaporization, or the next one is fusion, which is the backward process of the melting. Then the value of enthalpy of condensation and fusion is the negative of vaporization or melting enthalpy. Of course, relationships between enthalpy and internal energy of phase changes is like that. As you know, H is equal to U plus PV. So U is equal to H minus PV. For the vaporization, delta U sub V vaporization is approximately equal to delta H of vaporization minus PV, and in this case PV is going to RT, right, for ideal gas. So minus RT here. T is the boiling point, of course. This is about the vaporization. But no. Then let's go to the melting situation. Uh, the melting situation for liquid and solid. Of course, melting means the phase changes from the solid to liquid. Then in that case, the enthalpy is the internal energy, because PV term for liquid and solid is approximated by 0. Then it's time to go to the last variable to define the state, which is the composition. Change in energy term with change in composition, X of species I. I'd like to think about mixing and solution first, and then we'll go to the reaction, chemical reaction. Enthalpy of mixing, delta H caret with subscript mix, has only composition changes, of course, because the mixing means the same phase material is mixed to the same phase one. That's the mixing. So it's very simple. Delta mix is the enthalpy of the mixture after mixing minus the summation of enthalpy of the compounds involved in mixing in their pure state. So if you are trying to mix the water and ethanol, then it means this enthalpy should come from its mixture. However, this one is for pure water and pure ethanol, and you should multiply the composition, which is a kind of weight factor. So those difference is the delta H mix, or enthalpy of mixing. If your compounds involved in mixing has similar the intermolecular interactions, then delta H mix is 0. What does it mean? Right now you are trying to mix A compound and B compound, and intermolecular interaction between A and A, while between B and B, those two things comes from the pure state. And also the intermolecular interaction A and B are similar to each other, then delta H mix should go to 0. Because in terms of intermolecular interaction, nothing changes. So delta H mix should be 0. It means the enthalpy of mixture is the same as the summation of enthalpy of pure compound. However, if the intermolecular interaction between A compound and B compound is stronger than between A or between B, then delta H mix is not 0. You should think about the enthalpy of mixing. Let me change. Let me translate this relationship. If there are strong non-covalent attractive or repulsive interactions between two components, so it means A to B is much larger than this one, or very smaller than, or sometimes negative than the pure one, then we could consider the delta H mix seriously. So you should think about the intermolecular interaction. The next one is enthalpy of solution. For example, you are dissolving sodium chloride in water. So that is the solution process. Both composition and phase changes are involved. Composition, of course, changes 100% going to the 30% NaCl. Also, phase changes. Sodium chloride is what? Solid, and water is liquid. But the solution is, the phase of solution is liquid. So, some solid phase is converted to the liquid phase. The definition of delta H solution or enthalpy of solution is very similar to the definition of the mixing. This is the final one. This is the mixture, final one, after mixing. This is solution, final one, after you have dissolved sodium chloride in water, minus summation of the product of composition of each compound with its enthalpy in its pure form. L stands for solvent, liquid, solute. The S stands for solute, solid. So almost the same equations. Enthalpy of crystallization is negative of delta H solution. You know, crystallization or precipitation is the backward process of the solution process. One more things. We are still on the change in composition, but in previous chapters, previous slide, we have thought of mixing or solution. I mean physical mixing. However, in this case, I'd like to think about the chemical reaction. You could calculate the enthalpy of reaction by using two different methods. Okay, anyway, our target is to calculate the enthalpy of reaction, delta H caret of some reaction, R4 reaction. And here I'd like to emphasize the standard. The standard means 25 Celsius degree and 1 atmospheric pressure. So anyway, the first target for the reaction is to obtain the standard enthalpy of reaction. After you obtain this value, then you could change the temperature from the standard state, and you could change from the pressure from 1 atm standard state. Then you could calculate those values by using the previous slide method with a pressure change, with temperature change, with phase change. So in this case, I'd like to focus on standard state enthalpy of reactions. This standard enthalpy of reaction can be calculated by two methods. The first method is based on the enthalpy of formation, and the other thing is enthalpy of combustions. Those values are easily found here and there, internet, any chapter book or something like that. So to calculate the standard enthalpy of reaction, we need to have some information about the formation or about the combustion. So what is the standard enthalpy of formation or enthalpy of formation? This is the enthalpy change for the formation of one more of compound I from each element in their natural phase and state of aggregation. For example, CO2. CO2 can be made from just carbon plus oxygen gas. Carbon and oxygen gas are considered as elements in their neutral phase and state of aggregation, right? So the chemical reaction equation like C plus O2 is going to CO2. This kind of reaction, the enthalpy of this kind of reaction is easily found in some database. So we could use it. And that is the enthalpy of formation. The other thing is enthalpy of combustion. Also, we could find those values easily in some data book. Standard enthalpy of combustion is the enthalpy change for the reaction of oxygen with compound I. Combustion, right? It means oxidation of all species. For example, carbon can be combusted into CO2. The chemical reaction equation for the combustion is carbon plus O2 going to CO2. CO2 is a combustion product. Then we could use these reactions for calculating the standard enthalpy of reactions. Only for reactions involving molecular species containing no other elements except of carbon, hydrogen, oxygen, blah blah blah, but never mind about that. So from the examples you could get a deeper understanding about how to calculate the enthalpy of reaction from enthalpy of formation or enthalpy of combustion. But this picture is very important thing. Here, enthalpy of reactants, H1. Here, enthalpy of products, H2. So we want to calculate the difference between H1 and H2. Actually, H2 minus H1, which is going to the enthalpy, specific enthalpy of reaction. How can we calculate it? First, let's use the combustion pathway. Here is the reactant, and let me combust all reactants. Then finally we would have some combustion products like CO2, H2O, or something like that. And the enthalpy of this reaction, bypass reaction, is the combustion enthalpy, right? Combustion reaction, and this is the energy change with this combustion reaction can be calculated by the summation of the combustion energy or enthalpy of combustion of all reactants. So that is the delta HC reactant. Then we should drive the combustion products into the final product. Let me think about the backward direction of this process. So it means the product is combusted to combustion products, right? So the energy change would be delta HC of products from here to there. However, we should go from this intermediate to the final product. So the energy term involved in this fold process is minus delta H combustion. Then the summation of those two things, combustion energy of reactants minus combustion energy products, is going to the chemical the enthalpy of chemical reactions. Okay, so this one plus this one is going to this one. Or we could go to the other alternative pathway, that is the formation energy pathway. So the reactant molecules could be made from several basic elements like a carbon, O2, H2, or something like that, nitrogen. So let me say this intermediate is a library of elements, and when we go from the elements to the reactants with the minus formation energy, right? No. The plus formation energy from element to reactant. So to go from reactant to element or as the intermediate, the involved enthalpy term is going to minus delta H formation. Let's go to the second step. Right now we have elements, and then from these elements we could make the product. So the enthalpy of this process is delta HF or product. So summation of those two things, again delta H of formation of products minus delta HF the of reactants, delta H of formation of reactants. So the summation of those two enthalpy term is going to delta HR. Okay, we will calculate the enthalpy change of reactions, and here is the very basic the data. Let me check it. Table B.3 standard Gibbs energy of formation, enthalpy of formation here, and enthalpy of combustion. Let me focus on those two things, because by using those data we could calculate the enthalpy of reaction. Methane in gas phase, CH4, so this value there. Methane in gas phase, methanol in gas phase is like that, and also methanol in liquid phase is like that. You should recognize that the same species in different phases have the different values of formation and combustion energy. The same for water. Water get in gas phase or vapor, then this value. However, in liquid, another values for the formation energy and combustion energy. And also even for the combustion energy, the water is going to zero, because water is oxidized into water. That's it. So water is going to water. So water gas molecules has just zero combustion energy. However, water in liquid phase have some values about the combustion energy. Carbon dioxide like that, but the combustion energy of carbon dioxide is zero, because carbon dioxide is oxidized into carbon dioxide. The same thing, so zero. How about oxygen? Oxygen is basic element, right? So formation energy is zero, and combustion energy also zero, because oxygen is originally involved in the combustion, and oxygen is oxidized into oxygen, the same thing. So this should be zero. Then by using those data, I'll try to calculate the enthalpy of reaction. Okay. Let me calculate the delta HF, delta HR, I mean the enthalpy of reaction of these chemical reactions. CH4 is partially oxidized into methanol. So here is the reactant, CH4 in gas phase and 0.5 O2 in gas phase. Those two guys are going to the methanol in liquid phase. You should be very sensitive what kind of phase are involved. Gas phase, liquid phase, solid phase. Okay. So from here to there, then we could calculate the enthalpy of reaction. But we don't have this shortcut pathway, so I'd like to use two different detours to reach the final product from the initial reactant. This is the combustion pathway, and methane is combusted into CO2 and H2O as an intermediate. So for this process, you could assign the delta H of combustion of CH4 in gas with the stoichiometric coefficient 1. So this energy is involved in this combustion. Let's go to the O2, which is the other reactant. 0.5 O2. So stoichiometric coefficient by plus combustion energy of O2. However, the combustion energy of O2 gas is 0 because O2 is oxidized into just O2, the same thing. Product and reactant is the same, so delta H is 0. So you don't need to think about this one. Also, CO2 is or H2O or any other the combustion product can be converted to the final product CH3OH in liquid phase. The backward reaction of this process is combustion process. So this is the for this reaction from intermediate to final product can be described by stoichiometric coefficient of CH3OH with minus, I'd like to emphasize minus because this is the backward reaction of the combustion. So minus combustion energy of CH3OH in liquid phase. Then after summation of those three terms for CH4, for oxygen, for methane, then we could calculate the delta HR. So like that. And also let's go to the other pathway, which is the formation energy pathway. Methane could be made from carbon and hydrogen. Oxygen could be made from just oxygen. So from this elemental compound to the reactant, we could use the minus delta H formation of CH4, right? Because the backward reaction have delta H formation of CH4. So to go from CH4 to the intermediate, then we should put some negative sign in front of formation energy with CH4. How about the O2? Okay, minus delta HF formation of O2, but O2 is the basic element, so the formation energy is just 0. Then let's go to the second step. Then here is the intermediate, which is the element or basic materials. From those guys, we could make the final product, methane in liquid phase. So the energy involved in this process is 1. The stoichiometric coefficient of CH3OH with the formation energy of methane in liquid phase. Then after summing those all of this enthalpy, then we could calculate the enthalpy of reaction here. Okay, so the other one, methanol is combusted with oxygen. Then finally we could obtain CO2 gas and H2O liquid. You should recognize that this is not the H2O gas. If you have the gas phase H2O here, then it is the just exact combustion reaction process. So you could find the value of the combustion energy of methane for these reactions. That's it. But however, in this case, we have liquid phase H2O. This one makes a difference for the calculation. So let me check. reactant, product. This is the combustion pathway. So CH4 is combusted into some intermediate, so this is plus sign, plus combustion energy of CH4 with its stoichiometric coefficient. How about oxygen? The same thing. 2 by delta HCO2, but the O2 can be combusted into just O2. O2 is the same, specifically O2 in gas phase. Then this is 0. So you don't need to think about O2 here. I'll focus on the first CH4. The other thing, still we are combustion pathway, therefore H2O liquid is combusted into H2O gas, right? And we could find the value about this combustion energy. So this is the backward reaction to what I have said. So minus delta H combustion energy of H2O liquid. I'd like to emphasize the liquid by number 2. 2 comes from the stoichiometric coefficient of H2O liquid. The other thing is formation pathway, and in the same way you could calculate the enthalpy of reaction. In this slide, I'd like to give you very important comments about the formation enthalpy, combustion enthalpy, plus reaction enthalpy. Let me start with some example. I have a gas phase water, and its standard formation enthalpy difference or change was estimated at minus 241 kilojoule per kilogram mole. And here is the question. I have said about the gas phase water. Then my question is, how about the liquid phase water in terms of the formation energy? Is it different from the gas phase, or the same or identical to the gas phase in terms of formation energy? My answer is it should be different. So for water phase, liquid phase water, the formation energy or enthalpy is minus 285, which is different from the gas phase value 240. Then let me think about the difference between the values of gas phase and liquid phase in terms of formation energy. What is that? What is the meaning? The difference is the enthalpy of vaporization of water at 25 Celsius degree. Of course, this value comes from the gas phase, so gas is the final state after reaction or after process, and this is coming from the liquid phase, and this is the initial phase. So liquid to gas, it means evaporation or vaporization. So the difference of formation energy between different phases is going to some phase change enthalpy term. 44 is going to vaporization enthalpy. The first comments are belonging to this example. Let me read the statement. So standard enthalpy change of formation of species I and standard enthalpy difference of combustion of species I are functions of the phase of compound I. I have said the liquid phase water and gas phase water has different values of formation energy. Here also for the combustion energy. If formation energy or combustion energy data for two different phases are given, like gas phase and liquid phase, The difference is the delta H of phase change at 25 Celsius degree, because these values are obtained at standard state, including 25 Celsius degree and 1 atmospheric pressure. Okay, let's go to the second comment, exothermic and also endothermic. What is the meaning of exothermic? Exothermic means during reactions, we could observe some release of energy from the reaction, right? It means the energy level of product is lower than the energy level of reactant. So, enthalpy change of reaction is going to the negative value, because product minus reactant is going to the enthalpy term. Combustion, oxidation, hydrogenation, and hydrolysis reactions are belonging to these exothermic reactions. How about endothermic? Of course, its reaction enthalpy should be positive. Dehydrogenation, dehydration are typically endothermic. How about the isomerization reactions? Reactants and products looks very similar to each other. Usually, the reaction enthalpy is approaching zero. Of course, the value is something, like sometimes some minus value, some plus value, but the value is just around the zero. And let's go to the third comment. For chemical reactions, the reaction enthalpy at standard state is calculated per mole of reaction. I'd like to emphasize per mole of reaction. So the unit of the reaction enthalpy is kilojoule per mole of reactions. Be sure to write out the stoichiometrically balanced reaction explicitly and clearly, and keep clearly in mind the basis for your calculations. What does it mean? I'd like to give you an example. Here is the chemical reaction equation for ammonia synthesis. For example, 1 mole nitrogen plus 3 mole hydrogen, which is going to ammonia. But alternatively, you could vary the stoichiometric coefficient. For another example, 0.5 mole N2, 1.5 mole H2, and then which is going to 1 mole ammonia, or something like that. So let me calculate the reaction enthalpy at standard state for each chemical reaction equations. Delta H standard state of reaction is summation of the formation energy or enthalpy for each species, like formation energy of nitrogen, hydrogen, ammonia, with stoichiometric coefficient minus 1, minus 3 for the reactants, and plus 2 here. So, I mean, the stoichiometric coefficients are involved for calculation of delta H of reactions. Then N2 is going to 0 in terms of formation energy, because N2 is element in its natural state. How about hydrogen? It should be going to 0. The remaining one is the formation energy or enthalpy of ammonia, like that. And then final value is minus 90 kilojoule per gram mole. How about the second equation, second chemical reaction equations? Of course, I have said stoichiometric coefficients are involved here, and the stoichiometric coefficient of the second chemical reaction equation is the half of the stoichiometric coefficient of the first equation, even if they are the same equations. Therefore, the delta H of reaction is going to the half of the value of the first case. Here 90, here 45. What does it mean? We have the same chemical reaction equation, even if the stoichiometric coefficients are different. Then the reaction enthalpy was measured at different values. Why? I have said they are the same chemical reaction equations ultimately. So it means these values is normalized by gram mole chemical reaction. Again, so the unit is some energy per gram mole reactions. Okay, gram mole reactions. But the bases are different to each other. In this case, 1 mole of nitrogen. In this case, 0.5 mole nitrogen. So when you divide each values of reaction enthalpy by the stoichiometric coefficient of nitrogen in this case, then still we have the 90 for the first case, but the second case is going to the 90 after dividing the original value by the stoichiometric coefficient. So ultimately we have the same reaction enthalpy. Let me check more the third statement. So here this statement is saying that we should clarify and reveal the stoichiometrically balanced reactions. So when you are saying, okay, this reaction, the enthalpy of reaction of ammonia synthesis is minus 90 kilojoule per gram mole. I have said like that, but one more thing should be addressed. What is that? The balanced chemical reaction equation. So you are saying, I have this value, then you should say, okay, the chemical reaction equation is here with stoichiometric coefficient with 1, 3, 2 moles of each species. The total enthalpy change associated with the reaction equals delta H of reaction at standard state multiplied by the extent of reaction Xi. What does it mean? So actually I have said about that. The meaning of this sentence is the same as what I have said. The value should be divided by the stoichiometric coefficient. But in this statement, the statement is saying that the extent of reaction Xi. So let me say about that. If 100 gram mole nitrogen is fed along with an excess of hydrogen to a reactor, and 60% of the nitrogen is converted to ammonia, right? So let me calculate the Xi, or the extent of reaction. So the statement is saying that 60% of 100 gram mole nitrogen is converted to the product. So 60 gram mole per some time scale per the stoichiometric coefficient of nitrogen is the extent of reaction. So let me say 60 gram mole per some time scale. So the total enthalpy change equals the product of the extent of reaction with the enthalpy of reaction. Then 60 gram mole per time scale minus 90 kilojoule per gram mole, which is going to about minus 500 kilojoule at 25 Celsius degree. Let me calculate the same thing for the second balanced chemical reaction equations. Of course, in this balanced chemical reaction equations, the stoichiometric coefficients are different from those in the first case. Everything is the same, 100 gram mole, 60%. So let me calculate the Xi value in this case. 60 mole per time scale, but we should divide this value by 0.5 instead of 1. So the extent of Xi is 120 gram mole. then the product of extent of xi with the reaction enthalpy at standard state is going to the same value which was calculated in the first case here, minus 5500 minus 5500 minus 5500 at 25 Celsius degree. So actually this is the same chemical reaction equations. So please write down the balanced chemical reaction equations when you have said about the value of your reaction enthalpy. Very important comments were presented in this slide. Okay, then for chemical reactions we have calculated the enthalpy terms. And how about the internal energy? As you know, H is equal to U plus PV. So in the same way, delta H is equal to delta U plus delta PV. For liquid or solid phase, the change in pressure and volume, this one, with chemical reaction is very small because this is liquid and solid. So the second term is going to 0, then the internal energy is approximately equal to the enthalpy of reaction. I'm saying about the reaction. Internal energy of reaction is equal to enthalpy of reaction. How about gas, especially for an ideal gas? As you know, PV is equal to nRT, ideal gas law. Temperature is constant because we are considering the change in enthalpy due only to the reaction. So we are interested in the moles instead of temperature as the state variables. So delta PV of reaction is equal to RT with delta N. So this is going to the second term. So for an ideal gas, the internal energy is approximately equal to the enthalpy of reaction minus RT, the delta change of the moles. Okay, until now we have calculated the change in internal energy and enthalpy when one of the state variables are changed with the others fixed. For example, when you are changing the pressure, then you should fix temperature and phase and composition to calculate the change in the energy terms. However, in this slide, I'd like to say about what happens and how to calculate the internal energy and enthalpy when everything is changed. Pressure changes at the same time. Temperature is changing and also phase is changing. Sometimes moles are different. So here I'd like to give you some pictures. The most important thing is the energy terms are the state functions. State functions. It means they are not functions of the path of the system got to that state. So let me check this schematic picture. So x-axis is the state, means state variables, pressure, temperature, phi or phase. Y-axis is the enthalpy. And I'd like to calculate the enthalpy change from here to there. This is the reference point, the state of which is defined by pressure of reference, temperature of reference, and phase of reference. And the target point or target state is some pressure, some temperature, and some other phase. So I'd like to calculate the enthalpy change of this point to that point. That is to say, the length of this one. All right? If we can go directly from this point to that point, it is great, because the calculation process is just one step for calculating the delta H. However, it is impossible. So I'd like to travel some multiple steps like this one, this one, this one. And then I will sum all of the enthalpy terms of each step. Then I'd like to calculate the delta H between those two states. How can we do it? This one, I mean the direct change of the reference point to the final or target point is the same as this kind of detour pathway. Of course, pathway are different. However, the change in enthalpy or internal energy should be the same, independent of the pathway, because U and H are state functions. So instead of direct pathway, I'll go to the three-step pathway, detour pathway. So let me do it. At the very first time, reference pressure, reference temperature, and the phi or phase reference. Then at the very first step, I'd like to change only pressure. P reference is going to the target pressure. Then you could calculate the difference. You have learned about that in the previous slides. Previous slides. And then it's time to change the temperature. So T reference is going to the target temperature. And then let me change the phase. So phi reference is going to the target phi. Then please try to calculate the enthalpy change of each steps here, here, here. And the summation of those three enthalpy change, then we could calculate the total or overall enthalpy between the target point and the reference point. In the second schematic picture, I am saying the same thing. In this case, the initial state is state 1, and then the final state or target state is state 2. So I want to calculate H2 minus H1. In this case also, please change temperature, then change phase, and change pressure one by one. Please try to follow one by one change. Here's some statement, but I have said about that with these pictures. Okay, here is the, of course, example 6.8. Enthalpy calculation. Enthalpy of vaporization of water at high pressure. What is the enthalpy change associated with vaporizing water at 10 bar? That is the question. At 10 bar, the saturated temperature is about 180 Celsius degree for your information. Several things are given to you. Then by using those values, you should calculate the enthalpy change for vaporization at 10 bar, not just 1 bar of something. Okay, here is the given data. I'd like to explain about that. At each normal boiling point, it means 100 Celsius degree at 1 atm or 1.01 bar. The vaporization of energy or enthalpy of vaporization of water is this value. This value is given at the normal boiling point. Okay, what is our target? We want to calculate the vaporizing enthalpy term. So you can say, okay, the value is given here, but no, this value is about 1 bar, not 10 bar. The other thing is CP, heat capacity, pressure constant heat capacity of liquid water, not gas water, liquid water, it should be emphasized, which is 4.19 kilojoule per kilogram Celsius degree. And also Cp of water vapor. In the previous sentence we had said about the liquid water, but in this sentence water vapor instead of water liquid was given to you. The specific volume of liquid water, not gas water, liquid water was given to you at 180 Celsius degree, which was the saturated temperature at 10 bar. Okay, so let me give you an example, the explanation. What's the evaporation? Evaporation means vapor is going to the gas or vapor. No, liquid is going to vapor or gas. In this question, we should fix the pressure at 10 bar. So, what we should calculate is the evaporation from liquid to vapor of pure water at 10 bar, not at different bars like 1 bar or something. So let me start for calculation. Let me say this is the liquid domain and this is the gas domain. The starting point is the liquid water at 10 bar, and the target point or final point is gas phase water at 10 bar. So we want to calculate the difference between those 2 points, right? And in this liquid coordinate, we have temperature here and pressure here. So the starting point is liquid phase water at 10 bar and at about 180 Celsius degree at its saturation temperature. Then first thing I'd like to do is change the pressure from here to there, 10 bar to 1 bar, because we have the information about the vaporization enthalpy at 1 bar, or actually 1.01 bar. So I have changed the pressure from 10 bar to 1 bar. So this change is V delta pressure. So in the liquid case, so V delta P is, what's the delta P? 1 bar minus 10 bar and the specific volume. So it is going to minus 1 kilojoule per kilogram, like that. And then the next step is to change the temperature from 180 Celsius degree to 100 Celsius degree. How can we measure the enthalpy change? Of course, enthalpy change could be calculated by Cp delta T. So Cp of liquid water, I'd like to emphasize the liquid phase water because we are on the domain of liquid, with delta T. So we could calculate the value about this step. And then each time to change the phase from liquid to gas. So let me say this is the gas domain. Pressure, temperature, curve here, and we'd like to change the phase from the liquid phase water at 1 bar 100 Celsius degree and to the gas phase of water at the same 1 bar, the same 100 Celsius degree. What is this jump? Means how can we quantify this jump? This jump is about the phase change. Actually liquid to gas, so vaporization energy, delta H. So delta H was given to you like that. And then again, let me move the temperature from 100 to 180. Then moving this state by changing the pressure from 1 bar to 10 bar. So how about this value? Of course, temperature difference is going to Cp delta T. So you could do it. And for the last step, the pressure is changing. No change in enthalpy for ideal gases or low pressure gases. You have learned about that. So this is drawn for small delta P for real gas. So we have 1, 2, 3, 4, 5 steps. It means we have 5 values of enthalpy change. Then summation of all things, -1, -335, plus 2259, plus 152, and 0 is going to some values of the vaporization of water. This value is the enthalpy change associated with vaporizing water at 10 bar. The basis for the calculation of internal energy and enthalpy are different. For example, enthalpy change for a reaction, reaction enthalpy, which is based on per mole of reaction. Enthalpy change for temperature change of reactant, per mole of reactant. Enthalpy change for dissolution, per mole of solute. Enthalpy change for temperature change of solution, per mole of solution. It means the bases are different for the enthalpies. So, with a change in chemical composition, calculate the internal energy and enthalpy rather than, just some non-normalized value of internal energy and enthalpy should be used rather than specific enthalpy and specific enthalpy and specific internal energy. The unit of specific energy term is kilojoule per mole, right? However, U and H is just kilojoule, something like that. So when you are trying to calculate something, it is better to use non-specific energy terms instead of specific energy terms. Here is the example 6.9 about the enthalpy calculation. Enthalpy of reaction at high temperature. Methane is combusted in the presence of oxygen, which is going to CO2 plus water. It is a kind of the combustion reactions of methane. Also, the state is, or the condition of this combustion reaction is 500 Celsius degree and 1 atm. Let me try to calculate the enthalpy change associated with this reaction per gram mole methane. Some values are given to you, and the first one is Cp, the constant pressure heat capacity in kilojoule per gram mole Celsius degree. Methane, oxygen, CO2, gas phase H2O, and liquid phase H2O. The heat capacity was described by some polynomial equation of temperature. Two more information are there. The first one is vaporization enthalpy at the standard state. This value. The other thing is combustion enthalpy of methane at the standard state. The value is about minus 900 kilojoule per gram mole at 25 Celsius degree, because this is the standard state. Plus, one more thing, H2O liquid phase as product. Usually, combustion reaction is going to the gas phase H2O. However, for this value, H2O liquid is used as the product. The chemical reaction equation for the combustion of methane is this one. So you could say, okay, the final value is here. However, this value is obtained at 25 Celsius degree and liquid phase H2O. Our target value is the same combustion chemical reaction equation, but the temperature is different, like 500 Celsius degree. Also, in the product, you could find gas phase H2O instead of liquid phase H2O. Then, let me try to set up the pathways from reactant to product. Here is the schematic picture about the pathway. The starting point should be the reactant CH4, 1 mole, 2 mole of oxygen here, both of them in gas phases. What is the temperature and pressure for this reactant? 500 Celsius degree and 1 atm. After the reaction at 500 Celsius degree, we have obtained the product of the combustion reactions. 1 gram more CO2 gas, 2 gram more H2O gas at the same temperature and the same pressure. Our target enthalpy difference is between the product and the reactant. If we can go from the reactant to product, then it is very simple to calculate the delta H. However, it is impossible because many things are changed from the reactant to the product. So we should go step by step detour pathway. Here 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps are there. Let me check each step. First, I'd like to decrease the temperature from 500 Celsius degree to 25 Celsius degree. So the enthalpy change of this first step can be calculated by integrating of Cp with respect to the temperature. Temperature moves from 500 Celsius degree to 25 Celsius degree here. And this heat capacity is for the methane, and the other thing is oxygen, because we have 2 reactants. Then by integrating the temperature function, we could go to the enthalpy change for the first step. Why we are going to the 25 Celsius degree? Why not for other temperature? Because I'd like to use this value. This combustion enthalpy was given to you at 25 Celsius degree. So it is the reason I have changed the temperature from 500 Celsius degree to 25 Celsius degree. The other thing, like composition and pressure, are the same between the reactant starting point and this the second state. Then let's make some reaction at 25 Celsius degree. So finally we have CO2 gas and H2O liquid at 25 Celsius degree and 1 atmospheric pressure. H2O liquid comes from here. I'd like to use this value, so the final product of the CH4 combustion at 25 Celsius degree should include liquid phase H2O instead of gas phase H2O. So here is the liquid phase. Let me calculate the enthalpy change between those two boxes. We have 1 gram more CH4 and 2 gram more O2, then finally go to CO2H2O. So I'd like to use this value here and about the 1 gram more CH4. So it is going to this value. Then we have two compounds there, CO2 and H2O. I want to go to the 500 Celsius degree from 25 Celsius degree. We don't need to change the pressure for going to the final target state. Let me start with H2O first. Right now we have H2O liquid. So before going to 500 Celsius degree, we need to experience the evaporation step. So let me change the temperature from 25 Celsius degree up to 100 Celsius degree. The enthalpy between those two boxes can be calculated by Cp dt equation. So it is going to 11.4 kilojoule. Then right now 100 Celsius degree liquid there. In the following process, the liquid phase is evaporated into gas phase H2O. So this step is about the phase change. Fortunately, we have evaporation enthalpy there at 100 Celsius degree. So just to use this value, 40.65 with 2 gram more of H2O. Then we have the value for this step. Then right now, we have gas phase at 100 Celsius degree for water. Let me move the temperature from 100 Celsius degree to 500 Celsius degree. And then finally we are on the final state of water. So change temperature. Then use Cp dt equation. Then you could calculate the enthalpy change of this step. One more thing is left. We didn't touch the 1 gram more CO2 gas at 25 Celsius degree. So let me change the temperature of gas phase CO2 from 25 Celsius degree to 500 Celsius degree. Then we could use Cp dt equation. Why are water molecule and CO2 molecule going through different pathways? Because water should experience the phase change before going to the 500 Celsius degree. However, CO2 don't need to experience the phase change. CO2 is gas between 25 Celsius degree up to 500 Celsius degree. So we have a shortcut pathway for CO2. However, for H2O, we have 1, 2, 3 steps are there. Right now, we have calculated the enthalpy values or enthalpy change for all steps. Then let me sum all values. That is the H2 minus H1. This value for this one, this value for second, while the other thing. Then finally, we could calculate the total enthalpy change. That is the minus 800 kilojoule. This was calculated on the basis of 1 mole CH4, so I can say the specific enthalpy value of this combustion reaction at 500 Celsius degree and 1 atm is minus 800 kilojoule per 1 mole of methane. That's it for the example 6.9. Here is the summary table. What happens delta H and delta U when you change the one of the state variable? Pressure, when you are changing only pressure with others fixed, then you could find the delta H or delta U here. Temperature, phase, and compositions. Please try to read this summary table. This is the summary table, what you have learned from the former part of this chapter 6 about the energy balance equations.